All right, guys, last one right here. We'll just talk about the a couple of the FRQs that we have right here. Let's take a look at this one right here. Okay, exercise 12.1 to 12.4 refers to the following setting. Do taller students require fewer steps to walk a fixed distance? The scatter plot shows the relationship between X height in inches and Y number of steps required to walk the length of a school hallway for a random sample of 36 students in a high school. Okay, just going to write down n equals 36. We have it there. Least square. Here's the data right here. A least square regression analysis was performed on the data. Here is some computer output from the analysis. There's the residual right here. If you notice right here, remember from chapter 3, if we have the residual, this is supposed to be a scatter with no type of pattern at all. So this is actually good right here. This is a good residual plot that shows the linear model is appropriate. And right here, this is our histogram. Looks like a histogram of the residuals, right? Okay. All right, A, describe what the scatter plot tells us about the relationship between height and number of steps. All right, well, it looks like there is definitely a linear relationship. Let's see here, and what we said, the scatter plot reveals a negative, moderately strong linear relationship between height, inches, and number of steps. So yeah, and we know that because the scatter plot has a random scatter. So this right here reveals a negative, moderately strong relationship between height and number of steps. Okay. Let's take a look at letter B. What is the equation of a least square regression line? Define any variables you use. No problem. All right, so for part B, y hat is going to equal right here. Remember, the constant is 113.57. Okay, minus 0.9211x. And let's define everything. Okay, where y hat is going to be the predicted number of steps. Taken. And x equals height in inches. Okay, there we go. That's it. All right, let's look right here. Where y is the predicted number of steps and x is the height of the student in inches. Okay, all right. I think this is fine, but all right, the height of the students in inches, right? Because this was an experiment about seeing about 36 students. Okay. All right. So anyway, let's look at C. Identify the value of each of the following from the computer output, then provide an interpretation of each value. B sub 0. That is right there. That's the constant. So that's going to be right here. 113.57. So what does that mean right there? So when x is 0, the y is 113.57. Well, what is x? So when the height of a student is 0, so when a student has no height, the predicted number of steps that student takes is 113.57. All right, let's look at what the book says right here. If a student has a height of 0 inches, the number of steps to walk the length of the school hallway is 113.57 on average. Yeah, I should have kind of more said that. Remember, this is, number of steps required to walk the length of a school hallway for a random sample. All right, so that's good right here. So if a student's height is 0, right here, 0 inches, the number of steps to walk the hallway is 1/3. For a student to walk the hallway is 113.57. All right, B sub 1, that is the slope. That is negative 0.9211. Remember what I always said to do right here. All right, for the slope, it's negative 0.9211, right? So write that first, but just to help me out, I'm going to put that over 1. So what does that mean? That means right here for the x, which is, of course, the height, and the y, which is the y hat a predicted number of steps. So how could I explain this? For every 1 inch of height of a student, the predicted number of steps that they've taken goes down 0.9211 inches to get to the end of the hallway. All right. So for every 1 unit of height increase of a student, the predicted number of steps that they take to get to the end of the hallway goes down by 0.9211 inches. Something like that. Let's see what they say. Right here, pretty similar. For each 1 inch increase in height, the average number of steps to walk the length of the school hallway decreases by 0.9211 steps. The only difference is right here, I said predicted and they said average. Yeah, I thought we were just talking about the, yeah, so if we're talking about the regular regression line, then yes, okay, would be average right here, but I thought we were just talking about the, yeah, we're just talking about the least square regression, just the sample regression line. Anyway, I think what I said is fine. Okay, predicted. All right, so next one, S. So that is your standard deviation, remember, and this is, we're talking about, with standard deviation, we're talking about the number of steps. So that's the typical variation of the number of steps from the sample regression line to the population regression line. So it's 3.50429, right? So the proper way of writing that is right here. The actual number of steps needed to walk the length of the school hallway typically varies about 3.50429 from the predicted value, with the least square regression line using x equals height. All right, so what we were talking about right here, again, we're comparing the actual number of steps from the predicted number of steps, and that's what S is doing. Okay, so this is actual versus predicted. Standard error of B sub 1. Okay, so now we're talking about the sample regression line slope versus the population regression line slope and the typical variation. So we had right here it being 0.1938 is what this is, right? So right here, this answer right here was, if we repeated the random selection many times, the slope of the sample regression line would typically vary about 0.1938 from the slope of the population regression line. And then, you know, for predicting number of steps from height. So we're comparing right here the slope of the sample regression line and the typical, how much it would typically vary to the slope of the population regression line. Okay, so remember, slope of sample is like that, is B sub 1. Slope of population regression line is beta sub 1. Okay. All right, so that's that right there. 12.5 right here. First, they ask right here, they said that they did a transformation, right? So right here, let's read the whole thing. In a physics class, the intensity of a 100-watt white light bulb was measured by a sensor at various distance. Here's the scatter plot. Note the candela is a unit of luminous intensity in the international system of units. Now right here, this is not linear, it's a curved pattern, right? Physics textbooks suggest the relationship between light intensity y and distance x should follow an inverse square law. That is a power law model of the form y equals ax to the negative second. Okay, we transform the distance measurements by squaring them and then take the reciprocals. Here's some computer output and a residual plot from a least square regression analysis of the transformed data. Note the horizontal axis of the residual plot displays predicted light intensity. Okay, no problem. So, first of all, they said, did the transformation achieve linearity, give appropriate evidence? Well, the evidence would be your residual plot right here. And so we have to look, is this kind of like a random scatter? Looks like pretty good to me. Let's see what they're saying right here. Right here it says, yeah, the transform did achieve linearity because there's no leftover curve pattern in the residual plot. There's no curve pattern in the residual. It's just a general random scatter, so we're okay. Okay, and right here, by the way, just so we can have a clear right here. So this is the X is the predicted intensity. And the Y right here is, wait, hang on a sec. So this is our X. I'm sorry about that. Oh, I'm sorry. This is residual plot. Sorry, scratch that. We already have the graph right here. I just wanted to go and make a graph right here. So X is distance and the Y is intensity. Now in this particular case though, be careful. So when we do this, this new little thing right here, it's actually going to be x to the negative second right here. Okay. So what's the equation of the least square regression line? Define any variables that you use. All right, so it tells us right here actually distance to the negative second. So we're going to go and say right here for part B. Okay, so we have right here y hat is going to equal right here the constant, which is negative 0.000595 plus 0.299624. Now it's distance to the negative second. Distance, remember, is right here, the x. So that's going to be right there, x to the negative second, where y hat is going to equal the predicted intensity of the light bulbs right here. And x is going to be right here, the distance in meters. All right, let's see how the book had the answer, something similar right here. Yep. Okay, they put 1 over x squared, but x negative 2 is fine, where y is intensity, x is distance. Perfect. Okay, C. Predict the intensity of a 100-watt light bulb at a distance of 2.1 meters. Okay. All right, so the distance is 2.1 meters. So we're trying to figure out the intensity right here. So in this case right here, we have x is going to equal 2.1. So we have, remember, y hat equals negative 0.000595 plus 0.299624 times x, which is 2.1 to the negative second right here. All right, so we would just get this right here. We plug it all in. All right, in the calculator, you can just put this all in, and we end up getting what right here? They rounded that to 0.3, so if you want to do that, that's fine. And you get 0.0674. All right. All right, so 0.0674, and we're talking about candelas, which is a type, that's the unit of intensity. All right. All right, guys, hope this helped.